Hi there, Calculus 3 students. This is Mr. Lewit making yet another video. This video could be a little bit long, so you're going to need to set aside some time to watch this video. I would say at least an hour. This video could be longer than an hour, okay? And let me see here one moment. So for those of you who always think that I have pumpkins for my desktop wallpaper, that's not always true. This is a Carpathian wolf dog. It's about, I believe, genetically it's about 75% German Shepherd and 25% European gray wolf. A very beautiful animal. Unfortunately, he's not mine, but I saw this picture on the internet and I fell in love with him, so I decided I'm going to put this on my computer, for at least a few weeks. Or, well, a couple of weeks, whatever. Anyway, so you see, sometimes I really don't have pictures of pumpkins on my computer. I usually do, but sometimes I have other stuff. Okay, so enough fun and games. Let's talk about some serious mathematics. Okay, let's look at problem 62. A student in the class brought this problem to my attention, and he said he does need some assistance with it, so let's talk about how to do this problem. Okay, excuse me. Find the absolute maximum and minimum values of the following function in the closed region bounded by the triangle with vertices 0, 0, 0, 4, and 2, 4 in the first quadrant. And the function is f of x and y is equal to 2x squared minus 8x plus y squared minus 8y plus 7. Okay, so we're going to approach this problem the same way we would approach any maximization or minimization problem. However, there is a little bit of a restriction here. Excuse me. The restriction is that we're looking for maximum and minimum values within a very specific region of the xy plane. So initially, when we first start to solve this problem, we treat it the same way that we treat any other maximization or minimization problem, but at the end, there is that extra step. There is that extra step because of this extra information that we have here. So, let's give it a shot, okay? Again, guys, let's use Mathematica to make this process, a little bit easier. Let me just move this over. Okay, so we have f of x and y is equal to 2 times x squared minus 8 times x plus y squared minus 8 times y plus 7. Okay? Now, of course, we could use Mathematica to find the partial derivatives. That's probably not really necessary in this case because we're dealing with a polynomial function, and it's really easy to differentiate polynomial functions. You just use the power rule. I mean, it's really easy. So we can do that. We can do that by ourselves. I don't think we really need Mathematica, to help with that. Okay, so the partial derivative of f with respect to x is going to be 4 times x minus 8. And of course, the derivative of this with respect to x is 0. The derivative of this term with respect to x is 0. The derivative of this term with respect to any variable is 0 because it's a constant. And actually, from the point of view of x, these are constants too, right? So that's really easy, okay? That's pretty simple. And let's see. Fy of x and y, that's going to be 2 times y minus 8. Excuse me. Okay, so now we should find the mixed partial derivatives. The next step is to find the mixed partial derivatives. Okay, so it's going to be fxy is a function of x and y, and that's we take fx and we differentiate with respect to y. So we look at this right over here. We look at this expression. We look at this expression right here, the derivative of f with respect to x. Well, actually, it's the partial derivative of f with respect to x, to use proper terminology. And I have to differentiate that with respect to y. So what is that? That's really easy. That's going to be 0. And then the derivative, okay, the partial derivative of f with respect to y, we differentiate that with respect to x. And that's also a function of 2 variables. And we look at this expression right here, and if we differentiate that with respect to x, well, that's also going to be 0. And by the way, it's not a coincidence that the mixed partial derivatives are equal to each other. 99.99% of the time, they will be equal to each other. They will be equal to each other like 99.99% of the time. There are some weird exceptions where the mixed partial derivatives are not equal to each other. We will not encounter those in this course. Those are very weird functions that mathematicians will explore those functions in much more advanced courses. And I don't think I would teach a course like that. I could try, but that would be very difficult. So those are very, very advanced courses. So for a course like this, the mixed partial derivatives are always going to be equal. So if partial fxy is equal to 0, you know that partial fyx is also going to be equal to 0. Okay? So for this course, that's always going to be true. Okay, so what is the Hessian matrix? Well, we do need to know that eventually. So our Hessian matrix is going to simply be, well, there are different ways of defining it, but we could do this. We could do, how do I want to define this? Well, okay. X and Y, because X and Y will have specific values. So that's going to be fx, xy, fxy, xy, fyx, xy, and finally fyy, xy. Okay? And what does our Hessian matrix look like? Oops, yay. Sorry, a little mistake, a little typo. Okay, what does our Hessian matrix look like? By the way, that semicolon is very important. If you're going to combine 2 or more commands on the same line, and from Mathematica's point of view, this is one line, you need to separate your commands with semicolons. Otherwise, you're going to end up in deep water and having big problems with your mathematical work. Shift Enter. Oh, I see. What just? Oh, you know what? I didn't. Oh, I see. Okay. I see what the problem is. Okay. Sorry. Okay. What I forgot to do, fxx, xy is equal to, if I differentiate with respect to x, again, this is going to be 4. Sorry about that. And then fyy, x and y if I differentiate this again with respect to y, this expression right over here, that's going to be 2. Sorry about that. Okay, so let's start that over again. Clear Hessian. Let's do this one more time. Yeah, this should be fxx. Hold on one second. Clear that one more time. Okay, the Hessian matrix contains the second order partial derivatives. Sorry about that. Not the first order partial derivatives, the second order partial derivatives. I spent so much time talking about the mixed partials that I kind of ignored, the regular, the regular second order partial derivatives. Okay, so let's do this one more time. Let me just clear the Hessian. So I'm starting with a clean slate. There we go, Shift Enter. Okay, there we go. There we go. So for this problem, the Hessian matrix, regardless of the values of x and y, is always going to have this form right over here. The determinant of the Hessian matrix is going to be 4 times 2 is 8, minus 0 times 0, 8 minus 0 is 0. So this is going to be 4 times 2 minus 0 times 0. Okay, and we know that the answer is going to be, I see what the problem is. Okay, there we go. So yeah, Hessian is actually a function that takes 2 arguments, x and y, because that's how I defined it. Hessian is really a function that produces a matrix. It's not just a matrix. So yeah. Okay, so anyway, getting back to what I was saying, the determinant of the Hessian matrix is going to be 8. Okay, so let me erase that and do that one more time for people who are having a hard time following this. The determinant of the Hessian, that's not going to work because Hessian requires 2 inputs, 2 arguments, x and y, or whatever you want them to be. X and y, you can call them whatever you want, A and B, or C and D, or whatever you want to call them. And remember, that's going to be 4 times 2 minus 0 times 0. That's how you find the determinant of any 2 by 2 matrix, actually. So we know that's going to be 8. Therefore, well, your textbook calls it D. Determinant, D, whatever you want to call it, it's really the same thing. Okay, so this is important. We see that the determinant of the Hessian matrix is bigger than 0. So that means that any critical points that I find are not going to be, not in saddle points. They are not going to be, I was thinking inflection points. Okay, that's different. Any critical points that I find are not going to be saddle points. They must be, now take a look at these derivatives. Take a look at, take a look at fxx. It's positive. Take a look at fyy. It's also positive. So if fxx and fyy are both positive, that means that I'm dealing with local minimum points. Okay? They must be local minima points. They cannot be local maxima points because fxx and fyy are both greater than 0, which means the function is increasing after immediately after a point, or I should say immediately after you step off of that critical point, which implies that the critical point has to be a local minimum point. Okay. So we know we're dealing with a local minimum. So the next step we have to do is this. Fx, x and y, 4x minus 8, fy, x and y, 2y minus 8. Well, that's pretty easy to figure out. I don't think, hey, my dog's coming for a visit. Okay, so this is pretty easy to figure out. Okay, so 4 times 2 minus 8 is equal to 0. So x has to be equal to 2. Okay, that's easy. And here, you know, if I'm setting this equal to 0, okay, so I have 2 times 4 minus 8 is equal to 0. Remember, when you find your critical points, guys, fx and fy have to be set equal to 0. So 2 times 4 minus 8 is equal to 0. Okay. So then y has to be has to be equal to 4. Okay. So that means, here, let me define that. Minimum is equal to x is 2, y is 4. Okay, so that's going to be a local minimum. That's going to be a local minimum. Now let's go up here. Let me see something. That's actually part of our triangle. That's actually part of our triangle. That's not an accident. That's actually part of our triangle. Notice that this is actually part of the triangle. Ugh. That is actually part of the triangle. 2, 4 is one of the points of the triangle. Okay. So what I would have to do here, let me see. Okay, I have the function f defined. This is f. So f of 2 and 4 is equal to negative 17. Okay. So this is the extra step I was talking about. What about 0, 0, and 0, 4? I have to test these points. F of 0, 0 is equal to 7, and f of 0, 4 is equal to negative 9. So what is the lowest value? The lowest value is negative 17. And what is the largest value in that region? The largest value is going to be 7. The largest value is going to be 7, and the smallest value is going to be negative 17. Okay, my dog is up to something. So high maintenance. Okay. On the given region, the function's absolute maximum is 7. The function assumes this value at 0, 0. Determine the absolute, wait a minute, that was, Okay. Determine the absolute maximum value of f. Oh, I see. Okay, I see. That's okay. So I think this is a typo. I think they're talking about the minimum value of f. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. On the given region, the function's absolute minimum is, well, we can see from the Mathematica worksheet, it has to be negative 17. And the function assumes this value for 2 and 4. X is 2, y is 4, okay? Now here's the deal. So you might be tempted to say, wait a minute, Mr. Lewit, why did I have to do all of this calculus work? All I had to do was look at these 3 points, all right? All I had to do, 1 second. Let me change one thing here. But Mr. Lewit, all I had to do was just look at these 3 points. There was no need to figure out all those partial derivatives, and there was no need to figure out the Hessian matrix, or what your textbook calls the D value, which is really the determinant, et cetera, et cetera. Okay. For this particular problem, that's probably true. But I can tell you right now, that for other problems, okay, for other problems, you cannot just check the boundary values. You're going to have to check, and these are boundary values, by the way. The vertices of the triangle, those are actually boundary values. So for many of these problems, you cannot just check the boundary values or the vertices of some polygon, a triangle, a square, a rectangle, whatever. You're going to have to actually figure out the local minimum values and the local maximum values, because they could actually be greater or smaller than these values right here. You don't actually know that until you do the entire problem, okay? So hopefully that's not too difficult. I'm gonna skip around a little bit. I'm going to actually jump to 66. I believe I did a similar problem in the last video that I posted, but let's jump to problem 66. All right, and then we're gonna go back and look at some of the problems before 66. Okay. Okay, I actually did, excuse me, I actually did a similar problem in the last video that I posted for this class, but that's okay. We can do this problem. It's a Lagrange multiplier problem. All right, so this is a, although actually we might be able to solve it without using Lagrange multipliers. This is a classic Lagrange, the man's name was French. It's not Lagrange, it's Lagrange. Lagrange multiplier, all right, that's really bad. Multiplier problem. Okay, I'm writing with my trackpad, so it's a little bit awkward. Actually, we might be able to solve this problem without Lagrange multipliers. So here's the deal. Find the point on the plane 2x plus 3y plus z is equal to 8 that is nearest to the point 201. So what is the objective function? So the objective function is going to be the distance function. Now here's the deal. The distance function for this problem is actually going to be distance is equal to the square root of x minus 2 squared plus y minus 0 squared plus z minus 1 squared. Okay, so that's actually your distance function. However, this function is a little difficult to work with because of the radical. So instead of minimizing d, we're going to minimize d squared. And the theory is that if you minimize the square of the distance, you also minimize the distance. It's really going to be the same thing. So then we can just erase the square root sign or the radical sign. And of course, you don't really need to say y minus 0, just say y squared, okay? But there is a restriction. What is the restriction? The restriction is that x and y and z must belong to the plane 2x plus 3y plus z is equal to 8. Now, even though this is an example, let me try to spell this for you one more time. I think this is really an example of a Lagrange multiplier. Okay, one second. Multiplier. This is really an example of a Lagrange multiplier problem, but I think with a little ingenuity, we can figure out the answer without having to use Lagrange multipliers. So here's what I'm going to propose we do. Okay, first of all, what is my function? My function is distance squared x, y, z is equal to, hold on, I'm going to put the video on pause for a moment because something is happening at the other end of the house. So I will be right back. Besides, I have to stretch my legs anyway. Okay, we will be right back. Let's do a pause. Okay, so no big deal, just family stuff. Okay, I'm recording a video. This is not the time. Okay. Okay, so, okay. Let's get back to this. I'm recording. This is not the time right now. Okay. So let's get back to this. So we have the distance squared is going to be x minus 2 squared plus y squared plus z minus 1 squared, okay? However, think about what z actually represents. How can we isolate z? So think about, okay, we have 2x plus 3y plus z is equal to 8. So z is not just any variable we want it to be. Z has a restriction on it, and the restriction is very simple. Z has to be 8 minus 2x minus 3y. That's actually z. Okay, so z has a restriction on it. Z is equal to 8 minus 2x minus 3y. Okay, so we can define a new function. Let's just call it f. I'm going to erase the definition of the old f. F of x and y is equal to d squared x and y. Now z is going to be a function of x and y. 8 minus 2 times x minus 3 times y. So this is what f of x and y looks like. And we can simplify that. Let's simplify that a lot. Full simplify. Okay, well, let's expand it. Maybe that'll look a little bit better. Expand traditional form. Okay, so there you have it. So 5x squared plus 12xy minus 32x plus 10y squared minus 42y plus 53. And I'm going to store this in a new function, and we're going to call it g of x and y. G of x and y is my new function, and that is 5x squared plus 12xy minus 32x plus 10y squared minus 42y plus 53. So all I did was I copied this answer right over here. And that's now this is the function that I'm going to have to minimize. Why do I want to minimize it? Because I am looking for the point on the plane that has the minimum distance to this point. X is 2, y is 0, z is 1. I don't want the maximum distance, okay? I want the point that's going to give me the minimum distance. The maximum distance, that's infinity, okay? I want the point that gives me the minimum distance, okay? So I have to minimize this function. So let's see how we're going to do that. Solve. Well, first let's create our Hessian. Let's create our Hessian matrix. Let's see. For this one, I'm going to use a Mathematica shortcut. A and B are numbers. Those are going to be numbers. Table. The derivative of g of x and y. S and t are variables, and I don't know what those are yet, okay? So s could be x and y. 1 second. This has to be a curly brace. Sorry about that. Okay. And then t is replaced successively by x and y. Okay. So the Hessian, well, we'll worry about the exact values later. This is the matrix of the second order partial derivatives, you know, fxx, fyy, fxy, and fyx. Okay, so now we need to figure out gx and gy, the partial derivative of g with respect to x and the partial derivative of g with respect to y. Set those equal to 0. So how do we do that? So we're going to have derivative g of x and y is wait a minute, that's not going to work. With respect to x is equal to 0. Derivative of g of x and y with respect to y is equal to 0. And I'm looking for x and y. Okay, there's only one possible point. So this has to be the answer. So we probably don't really need the Hessian matrix, but let's use it anyway just to see what the matrix looks like. So Hessian of 17 over 7 and 9 over 14. Let's make that look a little prettier. Okay, so 10, 12, 12, 20. Okay, so what is the determinant of that matrix? It should be positive. Actually, it will be positive. The determinant is going to be 10 times 20 minus 12 times 12, which is equal to, actually, 1 second. Yeah, that will be positive, yes. Okay, sorry. That's 200 minus 144. So that's going to be 56. That's going to be 56. Okay, so what is the determinant of the Hessian of 17 over 7 and 9 over 14? And that is 56. So how do I know? Because it's going to be 10 times 20, 10 times 20 minus 12 times 12, okay, which gives you 56. So that means, well, and don't forget, if I look at the Hessian matrix, for these values, and let's make this look a little bit nicer. If I look at the Hessian matrix for these values, I can see that fxx, okay, this is fxx, and that's equal to 10, and then fyy is equal to 20. Those are positive, which means I'm dealing with a local minimum value, which makes sense because the d value is greater than 0, so I know I found the answer to the problem. So x is equal to, well, here we have to go back and okay, so I know x is equal, here we have to go back and flesh out the details. So x is equal to 17 over 7, y is equal to 9 over 14. Okay, z, so what is z equal to? Well, simple. All we have to do is go back to, what we did up here. If I can find what I did. Okay, 1 second. So what I did right here, what is z? Z is equal to 8 minus 2x minus 3y, right? So then all I have to do is 8 minus x, 1 second, 8 minus 2x minus 3y, 8 minus 2x minus 3y, so 8 minus 2 times x minus 3 times y, and that's going to be 185 divided by 119. That should be the answer. I'm going to cross my fingers. Let's see. Okay, the values of x and y are correct, but the value of z is incorrect. Okay, so okay, so it doesn't like my value. Oh, I'm sorry, it's 9 over 14. Okay, sorry about that. So 8 minus 2 times x. X is 17 over 7. Y is 9 over 14. Okay, so yeah, so there we go. Let me change that. 17 over 14. Okay, and that is correct. That is the correct answer. So that problem wasn't so terrible, right? Okay, I mean a little challenging, but not, it's not that big a deal. Let me pause the video for just a moment. Let me take a break and take something to drink, and then we'll move on to another question in the homework. Okay, so let me just pause my video, and I'll be right back.